HTTP compression is a capability that can be built into web servers and web clients to make better use of available bandwidth, and provide greater transmission speeds between both. HTTP data is compressed before it is sent from the server. Compliant browsers will announce what methods are supported to the server before downloading the correct format. Browsers that do not support compliant compression method will download uncompressed data. The most common compression schemes include gzip and deflate, however a full list of available schemes is maintained by the IANA. Additionally, third parties develop new methods and include them in their products, for example the Google Shared Dictionary compression over HTTP scheme implemented in the Google Chrome browser and used on Google servers. There are two different ways compression can be done in HTTP. At a lower level, a transfer encoding header field may indicate the payload of an HTTP message is compressed. At a higher level, a content encoding header field may indicate that a resource being transferred, cached, or otherwise referenced is compressed. Compression using content encoding is more widely supported than transfer encoding, and some browsers do not advertise for transfer encoding compression to avoid triggering bugs in servers. Compression scheme negotiation. In most cases, excluding the SDCH, the negotiation is done in two steps, described in RFC 2616, 1. The web client advertises which compression schemes it supports by including a list of tokens in the HTTP request. For content encoding, the list in a field called accept encoding. For transfer encoding, the field is called TE. GET/encrypted area HTTP/1.1, host, www.example.com, accept encoding, gzip, deflate. 2. If the server supports one or more compression schemes, the outgoing data may be compressed by one or more methods supported by both parties. If this is the case, the server will add a content encoding or transfer encoding field in the HTTP response with the used schemes, separated by commas. HTTP/1.1200 OK, date, Monday 25 September 2014 22:38 and 34 seconds Greenwich Mean Time, server, Apache/1.3.3.7, last modified, Wednesday 8 January 2003 23:11 and 55 seconds Greenwich Mean Time, except ranges, bytes, content length, 438, connection, close, content type, text HTML. Charset equals UTF-8, content encoding, gzip. The web server is by no means obliged to use any compression method. This depends on the internal settings of the web server and also may depend on the internal architecture of the website in question. In case of SDCH, a dictionary negotiation is also required, which may involve additional steps, like downloading a proper dictionary from the external server. Content encoding tokens. The official list of tokens available to servers and client is maintained by IANA, and it includes, compress a Unix compress program method, deflate a Euro compression based on the deflate algorithm, wrapped inside the zlib data format. XI a Euro W3C efficient XML interchange, gzip a Euro GNU zip format. This method is the most broadly supported as of March 2011. Identity a Euro no transformation is used. This is the default value for content coding. PAC 200 gzip a Euro network transfer format for Java archives. In addition to these, a number of unofficial or non-standardized tokens are used in the wild by either servers or clients. BZIP2 a Euro compression based on the free BZIP2 format, supported by LIGHTTPD. LZMA a Euro compression based on LZMA is available in Opera 20, and in a links via a compile time option. PeerDist a Euro Microsoft Peer Content Caching and Retrieval, SDCH a Euro Google Shared Dictionary compression for HTTP, based on VCDIFF. Supported natively in recent versions of Google Chrome, Chromium and Android, as well as on Google websites. XZ, LZMA2 based content compression, supported by a non-official Firefox patch. And fully implemented in MGET since December 31, 2013. servers that support HTTP compression, SAP NetWeaver, Microsoft IIS, built-in or using third-party module, Apache HTTP server, via mod deflate, Hiawatha HTTP server, serves pre-compressed files, Cherokee HTTP server, on-the-fly GZIP and deflate compressions, Oracle iPlanet Web Server, Zeus Web Server, LIG HTTPD, via mod compress and the newer mod deflate, Ningsa Euro built-in, applications based on Tornado. If GZIP is set to true in the application settings, Jetty Server Euro built into default static content serving and available via servlet filter configurations, GeoServer, Apache Tomcat, IBM WebSphere, OWL Server, Ruby Rack, via the Rack Deflator middleware. The compression in HTTP can also be achieved by using the functionality of server-side scripting languages like PHP, or programming languages like Java. Problems preventing the use of HTTP compression. A 2009 article by Google engineers, Arvind Jain and Jason Glasgow, states that more than 99 person-years are wasted daily due to increase in page load time when users do not receive compressed content. This occurs when antivirus software interferes with connections to force them to be uncompressed, where proxies are used, where servers are misconfigured, and where browser bugs stop compression being used. Internet Explorer 6, which drops to HTTP 1.0 when behind a proxy a common configuration in corporate environments. Was the mainstream browser most prone to failing back to uncompressed HTTP. Another problem found while deploying HTTP compression on large scale is due to the deflate encoding definition. While HTTP 1.1 defines the deflate encoding as data compressed with deflate inside a zlib formatted stream, Microsoft Server and client products historically implemented it as a raw deflated stream, making its deployment unreliable. For this reason, some software, including the Apache HTTP server, only implement GZIP encoding. Security implications. In 2012, a general attack against the use of data compression, called CRIME, was announced. While the CRIME attack could work effectively against a large number of protocols, including but not limited to TLS, and application layer protocols such as SPDY or HTTP, only exploits against TLS and SPDY were demonstrated and largely mitigated in browsers and servers. The CRIME exploit against HTTP compression has not been mitigated at all, even though the authors of CRIME have warned that this vulnerability might be even more widespread than SPDY and TLS compression combined. In 2013, a new instance of the CRIME attack against HTTP compression, dubbed Breach, was published. A breach attack can extract login tokens, email addresses or other sensitive information from TLS encrypted web traffic in as little as 30 seconds, provided the attacker tricks the victim into visiting a malicious web link. All versions of TLS and SSL are at risk from breach regardless of the encryption algorithm or cipher used. Unlike previous instances of CRIME, which can be successfully defended against by turning off TLS compression or SPDY header compression, Breach exploits HTTP compression which cannot realistically be turned off, as virtually all web servers rely upon it to improve data transmission speeds for users. References. External links, RFC 2616, Hypertext Transfer Protocol HTTP/1.1, HTTP Content Coding Values by Internet Assign Numbers Authority, Compression with LIG HTTPD, Coding Horror, HTTP Compression on IIS 6.0, 15 seconds, Website Compression at the Wayback Machine, HTTP Compression, Resource page by the founder of VIGOSAG, Konstantin Rak, using HTTP compression by Martin Brown of ServerWatch, using HTTP compression in PHP, check HTTP compression, dynamic and static HTTP compression with Apache HTTPD, browser HTTP compression test.